Hello, everyone. I hope you all had a great time during the training course on life cycle assessment organized by International Solid Waste Association. My name is Dr. Ehsan Farouk, and I will be sharing my thoughts and experiences in life cycle assessment of waste to energy in Thailand. So before going towards the life cycle assessment of waste to energy, I will talk about that while waste to energy is a viable option for sustainable disposal of municipal solid waste. So, if we talk about the annual global municipal solid waste generation in 2012, it was around 1.3 billion tons, and which is expected, and it is predicted by World Bank that this quantity will increase to around 3.4 billion tons by 2050. On the other side, municipal solid waste composition is also becoming uh, more and more complex. So, if we talk about the composition of municipal solid waste, broadly it can be categorized in four different types, which is biodegradable waste, recyclable waste, non-recyclable waste, and hazardous waste. So, in biodegradable waste, mostly it includes kitchen waste, food waste, then wood waste, garden waste, and non-recyclable plastic. In recyclable waste, it includes paper, plastic, glass, and metals, both ferrous and non-ferrous. And in non-recyclable plastic, mostly those plastic that are hard plastic, that are uh, like bottle caps, mostly the hard uh, casing of different products that like perfumes or other different kind of things that come in very hard shells, uh, hard casing of hard plastic packaging. And the hazardous waste includes absorbent hygiene products, which are baby diapers, used baby diapers, used sanitary napkins, and then use condoms, etc. And also it includes clinical masks, etc. So these are all different types of waste components that are included in municipal solid waste. So if we talk about the complexity, so the left side of this figure, which comprises of biodegradable waste and hazardous waste, are more complex as compared to recyclable material and non-recyclable plastics. So why this quantity of waste is increasing and becoming more and more complex? This is because of the reason like quantity is increasing due to urbanization, population growth. It may be because of consumerism, because when people getting rich, they tend to spend more and more to improve their lifestyle. It also reflects in the income level of different countries. Like if you look at developed countries, their per capita waste generation is higher as compared to developing countries. And also the complexity of waste, which is maybe due to like proliferation of single use of plastics, and also like addition of advanced or new types of waste like e-waste. This is maybe due to the technological advancement, because when technology is becoming smaller, it becoming easier to dump with the normal waste streams, especially in developing countries, because developed countries have a very systematic waste management uh, uh, the sector. But in developing countries like Thailand and other Asian countries, the mostly like uh, mixing different types of waste is common practice by like common households. So these are some reasons that make the sustainable disposal of municipal solid waste quite complicated and challenging. So if we talk about sustainable disposal of municipal solid waste, around 40% of municipal solid waste is landfilled globally, and 30% of waste is openly dumped. So the waste quantity that is uh, treated through modern techniques, with modern waste to energy techniques, is only 11% out of the whole waste, the total waste that is generated globally. So if we compare, it is quite significantly low. Okay. So Besides waste generation and its disposal, sustainable disposal, there is an other issue that we face globally, which is electricity generation by using fossil fuels. So, if we talk about electricity generation, since last 2 decades, it's continuously increasing, which is like understandable because we are moving towards like more economic development and uh, growing more and more, growing technologically and economically both. And we need energy resources for that. So this is understandable that our energy is increasing, so that our population is increasing. So if more like it's we need more people, more food to feed more stomachs. Similarly, we need more energy to light more houses because our energies, our population is increasing. Our uh, we need more houses to accommodate that increased number of population. We need more hospitals. We need more schools. We need more infrastructure to give them a uh, considerable, uh, acceptable, satisfactory living standard. But the problem is most of the electricity since like still now, most of the electricity is coming from fossil fuel. So around 64% of electricity in 2022 was produced by using fossil fuels. Out of that, 23% was produced by using natural gas, 38% was produced from coal, and 3% was produced by using oil. So mostly global electricity dependence. This is not energy. Electricity dependence is on uh, fossil fuels by until 2022. So why waste to energy? Both unsustainable municipal solid waste like open dumps or unsanitary landfilling and electricity generation by using fossil fuels cause many environmental hazards and health issues, etc. And waste to energy is a common solution that can solve both the problems. It can sustainably dispose the municipal solid waste, and it can also produce electricity that would otherwise be produced by using fossil fuels. So this can be a promising solution and a waste to energy to solve both these problems simultaneously. But waste to energy also comes with a lot of challenges. These challenges are mainly because of two reasons. First is that waste to energy is a multidimensional and interdisciplinary process. So many different aspects are related to waste to energy, which are environmental aspects that focuses on the ecological impact and sustainability of waste to energy processes. Then economic aspect that examines the functional variability and economic implications of waste to energy impacts, because ultimately waste to energy is a business. So if someone is investing in it, he wants to get the most of it economically in terms of money. Then the social aspects, like uh, mostly in developing countries, at least in Asia, and specifically in Thailand, there was a campaign which was about no more power plants in our backyard. So people were protesting against waste to energy plants. They don't want it because it creates a lot of like bad odor and a pollution in the area where these plants are located. So there are many social aspects are also related to it. Then technological aspect that highlights the technological innovations and challenges related to waste to energy. And then finally the cultural aspect, that how people practice waste disposal or waste dumping, and what are their food culture and etc. So these all are related to multidimensional aspect of waste. Interdisciplinary is that many different kind of stakeholders are involved, especially like if I talk about mainstream audience, these are uh, of course the power plant owners, the waste to energy plant owners, because they are investing their mainstream audience, they are involved in it. Then policy people, government, they are involved because they have to make informed decision about whether the waste to energy technology or waste to energy plant that they are approving are environmentally, socially, culturally are viable or not. And then the downstream audience, they also are related to it, whether the waste to energy plant is uh, providing safe disposal of municipal solid waste for them, or the environmental burdens that are coming, or environmental emissions from the waste to energy plant is under the controlled limits or not. So these are all different kinds of uh, uh, stakeholders that are related to waste to energy plants. And then, of course, the research and development sector and academia, which are related to the technological aspect of waste to energy. So waste to energy is quite a complex process in itself. The second issue is the availability of vast range of waste to energy technological options in the market. So mainly waste to energy technologies are divided into two different categories: thermochemical technologies, which are more favorable to treat thermochemical feedstocks. I will explain what are these in the next slide. And then biochemical technologies. In thermochemical technologies, it includes incineration, pyrolysis, gasification, while biochemical technologies include anaerobic digestion, fermentation. Their output, the 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 products, I would say, we get from different waste to energy technologies are also different. From incineration, we get heat, and that heat is used to produce electricity. From pyrolysis, we get high quality fuels, mostly oil, pyrolysis oil, then biochar and pyrolysis gas also. And then gasification gives us syngas, which is very high quality gas, fuel gas, and it can directly be used in gas turbines to produce electricity. And from biochemical technologies, we get outputs from anaerobic digestion. We get biogas that can be used in reactors and like combusted in reactors, and then can be used to produce, and that the heat from that reactors can be used to produce electricity. And then from fermentation, we get fuel grade bioethanol and other biofuels, etc., and can be used to produce different biochemicals as well. So when I say thermochemical feedstocks or biochemical feedstocks. So this was a study that we have done uh, in 2021, where we identify that which waste to energy, waste composition. These waste compositions are according to IPCC waste categorization. So so which components we figured we estimated that which components of waste municipal solid waste stream are more favorable for each different type of waste to energy technology. So for anaerobic digestion, here F stands for favorable and U stands for unfavorable. You can see for anaerobic digestion, only organic waste is more favorable, excluding waste, because wood waste is quite difficult to uh, it needs additional process to like process through anaerobic digestion. That is why it is not favorable. While incineration, in incineration only food waste is not favorable, while all other different waste composition are favorable to process through incineration. That is why incineration is mostly used waste to energy technology globally. Then there is pyrolysis, gasification, and esterification. This is different from biochemical and thermochemical. This is physiochemical transformation of waste into energy. Mostly it is used for uh, used cooking oils, or different types of uh, oils that can be converted into biodiesel. So we will just focus mainly on anaerobic digestion and incineration, because these are the most common practices uh, globally. So now I will move towards waste to energy of municipal solid waste. So this was a study that we have done recently. Uh, in this study, we performed economic feasibility assessment based on life cycle assessment. So in this economic feasibility assessment, we considered environmental assessment, social assessment, and financial assessment. But today I will just focus on environmental assessment. And for this environmental assessment, we use life cycle assessment. So as you all know, life cycle assessment have four different phases. First is goal and scope definition. Second is life cycle inventory. Third is life cycle impact assessment, and the fourth stage is interpretation. All these phases are interconnected and they are iterative process. So, and the application of life cycle assessment is quite vast. It can be used to assess product, technologies, product development, product improvement, strategic planning, policy making, etc. So I will focus on the life cycle assessment of waste. So in first phase, I think most of the time, if you want to perform a life cycle assessment of waste or any product, the most of the time that you should spend is on goal and scope definition of the life cycle assessment study. Because if you are clear with this stage, if you are clear with your goal and the scope of life cycle assessment, it will be very easy for you to conduct a comprehensive and useful inventory. Otherwise, you will just get lost in inventory analysis. If you are not clear with your scope, you're not clear with your goal, if you don't know what are your system boundaries, then it is very difficult to get a very comprehensive and satisfactory inventory to perform your life cycle assessment. So that's why I suggest that if someone wants to do life cycle assessment, they have to understand that why they want to do life cycle assessment and what they want to do and for whom they want to perform this life cycle assessment study. So in this study, in this life cycle assessment, I will just talk about the environmental uh, feasibility of different waste to energy technologies. So our goal is clear that we will just talk about the environmental feasibility of different waste to energy options within Thailand. So this was the main goal of life cycle assessment. Sorry. And then we have to define a functional unit. And in this case, the functional unit was defined as management of 1 ton of municipal solid waste. Why management of 1 ton of municipal solid waste and not uh, the generation of electricity from 1 ton of waste? Because waste to energy is not just uh, like it is a multifunctional process. It has many different functions because we get recyclable waste from it, we get other value added products from it, we get electricity that can be replaced that will replace grid electricity. So this process have many different functions. So that's why we cannot just target one function. We have to include all the functions that are related to waste to energy. That's why management of 1 ton of municipal solid waste is a better functional unit for waste to energy. Then for analysis, for assessment, we consider three different types of waste to energy technologies. The first one is municipal solid waste anaerobic digestion for energy recovery and value added products. Second one is municipal solid waste incineration for energy recovery and value added products. And third one is an integration of municipal solid waste incineration and anaerobic digestion for energy recovery and value added products. So see, this value added products, this is the reason that we choose this functional unit. So everything is connected. So you have to be clear that what you want to do and why you want to do it, and what would be your system boundaries and your objective, your uh, uh, the systems that you are studying. They also define. Uh, they are also defined by your goal and your functional unit that you are selecting. So for the process flow, the system boundaries for all three waste to energy technologies, it also we actually excluded transportation and collection of waste because of an assumption that all three waste to energy options that we are studying are considered as mutually exclusive, which means it is a comparative life cycle assessment where we have to compare that which one is the most favorable. So that's why it also explains that only one waste energy option will be considered, which will be the most environmentally feasible for any, let's say, for a municipality. Okay, so if the waste energy is destined to be planted in the same municipality, so the emissions for collection and transportation of waste will be same for all three. So it's just an extra work if you are doing a comparative analysis. But if you are doing just for one technology and you want to see the whole environmental emissions, you have to include all the like all the processes within uh, the waste to energy. Okay. So in the system boundaries for our life cycle assessment study, it starts from gate to grave, which means we get waste at the waste to energy plant. So the first step is municipal solid waste sorting and preparing, where recyclable materials are recovered. The wet organic waste is separated for anaerobic digestion, and the refuse waste, which is mostly non-organic waste, that is then uh, diverted toward landfilling. The wet organic waste then go under anaerobic digestion. There we get digestate, which turn into organic fertilizer, which is another value-added product which replaces uh, conventional fertilizer in the market. And from the biogas that is recovered from anaerobic digestion is used in biogas reactors and produce heat that which is used to produce electricity. And some of the electricity is used in-house for the to fulfill the electricity demand within the waste to energy plant, and the remaining is sold to grid. Similarly, for incineration, it is like easier, like more less complex as compared to waste to energy and anaerobic digestion. Process starts with sorting and preparation, where we recover recyclable and the waste, which is mostly organic waste, kitchen waste, food waste, garden waste, etc., is diverted toward landfill. And then we get combustible waste from sorting, which is then incinerated in the reactors, and the heat it is used to produce electricity. And some bottom ash and fly ash is recovered, which is also diverted to landfill. The electricity that is produced is then sold. Some of the electricity similar to anaerobic digestion is used in-house to satisfy the energy needs in waste energy incineration plant, and the remaining is sold to grid. And the third one is a integration of both the uh, anaerobic digestion and incineration plant. So the most of the inventory, like foreground inventory, most of the data uh, 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 is obtained from literature by using top-down approach, because the data was not. It was when this study was conducted, it was COVID time, and it was really difficult to get data from the source. So we relied on secondary data, and the background inventory data was mostly used from EcoInvent 3 database, and some data was used by you from Thai National LCA database as well. So for foreground data, for waste to energy, for the life cycle assessment of waste to energy, you must uh, know the composition of municipal solid waste. Uh, and in Thailand, mostly more than 50% of waste is organic waste. And you also know, as recovery of recyclable waste and their replacement of virgin material by recyclable waste. You also must know the share of recyclable waste in municipal solid waste composition, as well as the replacement efficiency of recycled label material with the virgin counterparts. And this is the part where we perform life cycle impact assessment. Eight categories were selected due to their significance in the impact assessment results, which include global warming potential, fine particulate matter, marine eutrophication, water consumption, uh, fossil resources, freshwater eutrophication, and uh, yeah, water consumption, human health. So what is difference between life cycle assessment of waste for waste to energy and life cycle assessment of a product. So the first uh, difference is functional unit. For LCO waste, mostly we based on the waste treated or waste managed, like 1 ton of waste managed or 1 ton of waste treated through like some particular waste to energy technology. But on the life cycle assessment of products, we mostly the functional unit is mostly based on the unit product, like 1 kilogram of product produced, etc. The second difference is in system boundaries. So for life cycle assessment, there is no uh, straddle because it is not uh, produce like agricultural products or crops. It is just collected. So that's why it's not include production process. It's only include start from collection, transportation, then treatment and disposal, final disposal, end of life treatment. While for LCF products, it starts from the extraction of raw material or production of raw material, then uh, the production of the actual product, then use phase, and then the disposal. So you see in LCA, life cycle assessment of waste, there is no use phase. But in the LCA of products, there is the use phase is a major part of the LCA, the life cycle. Then the core products in life cycle assessment of waste, there are many core products. Like in my system boundaries, we have recyclable materials that will replace virgin counterparts. We have organic fertilizer that will replace conventional fertilizer. We have energy that can replace grid electricity. But in LCF products, they are mostly fewer co-products, and if there are some co-products, they are like uh, simpler and easy to allocate. Then their burden of distribution, right? The the life cycle assessment of waste varies by treatment methods. Like I showed you, there are multiple options for life cycle for waste to energy. But for production of process, if you are following one technology, it will be like if you're talking about production of some particular product, there may be just 1 or 2 technologies or 3 technologies, and the output is definitely the product that we are talking about, that we are assessing, right? And the avoided impacts, most avoided impacts. Mostly in waste to energy technologies, there are many avoided impacts. We allocate avoided. We give credit to our system from the avoided impacts of energy, that electricity that uh, we replace in the grid. Then the recycle products, the recycled material, and also some other value-added products like fertilizer. But in LC of conventional products, like LC of other products, we have less, the avoided impacts are less frequent, I would say. Then variability. In life cycle assessment of waste, the variability is very high due to temporal and spatial differences because uh, with even within a country, or even within one province, waste generation, the waste composition changes. Like if we talk about high income countries or lower income countries, the composition in high income countries is comprises more of recyclable waste, dry waste, like paper or e-waste or plastics, while in developing countries, like I just showed in Thailand, more than 50% of waste is organic waste and it's mixed. So it is quite complicated. So the waste generation, even we use incineration in uh, some European country or in Asian country, the impacts will be different. The process will be different. The considerations will be different for same process in different regions. There are very high level of variability in LCA of waste to energy in when we talk about temporal or regional special aspects. While in the LCA of product, maybe there will be some variabilities due to the grid mix, because electricity is always a big component of any production process. But other than that, uh, you you can I will just explain it simply that if you want to make coffee, you need coffee, right? Whether you make it in Asia or you make it in Europe. Similarly, if you make some product in Asia or Europe or any part of the world, the ingredients will be same. Only where those products are coming can be different. So this can cause some variability, but not as much as in LC of waste to energy. And then the end of life uncertainties. In life cycle assessment, the end of life uncertainties are high. This is also because the climatic conditions, when we dump waste in landfills or uh, maybe some controlled environment, then the emissions will be different. But if we go to in Asia, the climate is more humid and hot, so the emissions will be different from the landfills. But in colder region, the pattern of emissions will be different. While in LC of products, the end of life uncertainties are low because for a single product, we know what is the fate of that product in the end of life. If it's a PET bottle, right, we know it can be recycled. If it's some other kind of product, we can know that it can be dismantled and different components can be used in different manners. So these are some differences in LC of waste and LC of products. So now I will move to the software part of the lecture. So I will show you how you can model and what kind of challenges you can face when you are doing uh, life cycle assessment modeling of waste to energy in SEMA Pro. So let me show you that. Okay, so when you will open SEMA Pro, you will get this window first, and here you can create a new process. So you can you can name your project as you like. So I will write as ISWA LCA training waste to energy. So when we open it, we have to click it, then our process will be created. Okay, so you will get this message that your project is already created. And then you have to select all these inventories. And after selecting, you can just simply click on processes. Then all your inventories will be selected. After that, you have to create a process. So our uh, process is waste to energy. So we will go to energy and you can simply create new category here by naming it ISWA LCA training waste to energy. The process is completed here. And in this process, then you can add no new categories. These categories you have to follow your system boundaries or your process flow diagram. Like I will follow this because we are doing for incineration, so I will follow this process flow for incineration. So the process starts from municipal solid waste sorting. So I will start a process, municipal solid waste sorting, and I will see that what other outputs I am getting from this process. So I'm getting recyclables, combustible waste, and refuse waste. So let's just model it this way. So first, municipal solid waste sorting for incineration. We will click it, we will get this process here. So you just, before starting with this one, I will create one more process, which is the dummy process, mixed municipal solid waste, because we are not including uh, collection and transportation of waste, so there will be no emissions related to municipal solid waste that are coming into the plant. So we will only looking for the emissions that are uh, or environmental burdens that are from the waste to energy process itself and the disposal, the end of life of waste to energy process as well, but not the collection and transportation one. And that I already explained why we omitted that, why what assumption we made to skip that part. So this process is already made. You just have to click here and add new. When you start new, you will get on this window. In this window, you have to write what output you are getting from here. So there are multiple options. You can add outputs that we are putting into technospheres, like products and co-products. Then some outputs that are avoiding the other products, like what are the avoided products that we are avoiding from our products and co-products that we are getting from our process. So in this part, we will put our outputs like products and co-products, and here we will add those products and those products that we are avoiding from our process. And for inputs, we have to be sure that where we are getting. For this part, you have to understand your process. You have to go to see the process in person. That will be the best way. You have to look for everything, every stage of the process uh, carefully. So it will be easier for you when you are performing your life cycle assessment uh, on your computer, on your software. So you know that which input is coming from where. Okay. So if you are using water, you have to understand that this water is coming from, is this the process where the water is coming from? Is it groundwater? Is it surface water? Or is from the river? Or where? Just for this is just for example. Okay. So let's start with mixed. I have to click here. Mixed municipal solid waste for incineration. So you have to name your process, and maybe sometime it will give an error because maybe the name that you give your product is already existing in some database. So you have to change it. Okay. So for here, I will add 1,000 kilogram, or you can just go to ton, but I will go for 1,000 kilogram, which will be easier for entering other inventories in other processes. By this, there will be no input because we are just making it as a dummy process. We will save it and then close this one. Just to give a starting point, we will use mixed waste as an input in our process. So here, first we will add what we are getting. So just following our inventory data, this is the inventory for sorting of 1 ton of waste for incineration. So we are getting recyclables that are 98 kilograms, diffuse waste that is 418 kilograms, and then sorted waste, which is combustible waste, that we are getting 484 kilograms for incineration process. And then there is wastewater. So all the water that we are using for sorting is turned out as wastewater as well. So first we will add combustible waste for incineration. So this is 484 kilograms, if I'm correct. Let me just recheck. Yeah, 484 kilograms. Then we will add recyclables. With 98 kilograms of recyclables. And the last one is refused waste. Refused waste is 418 kilograms. And then we will do allocation on mass basis. and we will just allocate as much. We have 48.4, 9.8%, and this will be 41.8%, simply based on mass. So you can do allocation based on uh, physical properties or economic allocation. So if the products that we are getting, the outputs, products and co-products are in the same units, like they are in in terms of, if they are, we are getting products in terms of mass, so we can do allocation on mass basis. Or if we are getting products in terms of fuels, we can do allocation on energy basis, right? But if we are getting products and co-products in different units like mass and energy basis, so we can do economic allocation. That will be the best case scenario for allocation in that case. And then we will add our inputs. So first we will add mixed municipal solid waste, which is 1 ton. So that is coming from Technosphere. So we will just go to our process that we just created, energy, training, mixed. We'll select this and we will add it 1 ton. Okay. So this will be our first input. Second input is electricity. So for electricity, you have to go to energy. Okay. Energy. Then go to electricity by country mix, medium voltage, because when we use electricity in industry, we always use medium voltage electricity, because when we produce generate electricity is always high voltage. We transform it and then convert it to medium voltage, and that's why we're using transformation as well. And then you have to search for your specific country. Like this study is for Thailand, so I'm looking for medium voltage electricity for Thailand. Here it is. Okay. And how much electricity is 23 kilowatt hour of electricity. Next input is water. So you have to see which water you want going to use. If the water is from Technosphere, mostly in Thailand we use surface water or river water. So I will just go for input from nature. And then yeah, here we already have like water for process, and it is surface water. So I will just select this. And this is 32 uh, 32,000 kilogram or 32 cubic meter of water. So here we have in kilograms, so I will add 32,000 kilograms of water. The next input is diesel. So for diesel, for 1 ton of, no, sorry, we have to delete this line because diesel is from Technosphere. So input from Technosphere, material or fuel. We will go to here, this line, and then again we will go to materials. From materials, we will go to fuel, and then from fuel, we will go to oil and then find diesel. If you have diesel for your specific country, then you select that. In case we don't have the data for our or inventory for our specific country, we will select the rest of the world. This excludes some countries like this data. You can read the information, more information about your data here. So here you can see. So this data represents this data is for, I just saw it here and now I just forgot. Okay, anyways, you can look by yourself. So the data rest of the world, it excludes data for some European countries and some other high income countries. And uh, this will be like we have to select the the closest or the most true representative data for our case. So that's why we are selecting this one because we are doing for Thailand, and Thailand is a middle income country, which is not in the race of European countries or other high level income countries. So we can select rest of the world. Okay. And the other information about which database we are using, this is EcoInvent. You can get information from here. You see EcoInvent 3, and all the information is here as well. So we will select this and we will add the number, which is 1 kilogram of diesel we use here. And then we will see what other outputs we get. We get recyclable that we already add refuse waste, and then we get wastewater as well. So for wastewater, you have to go to emissions through water and then get wastewater and then add your quantity. And when you have done all this already, you can just save it, right? And then you just have to click on analyze. For analyzing, here we are doing because we are combustible waste, so we will add according to our functional unit. From 1 ton of we get 1 ton of mixed waste, we get 484 ton of combustible waste. Actually, you can add any quantity, but afterwards you have to adjust this according to your adjust this results according to your functional unit. So it is easier if you just add uh, the numbers according to your functional unit here already, then you don't have to do extra hard work. And then you have to select a impact assessment method. So these are European method. I will go for global and I will select recipe. And for impact assessment, you can go for uh, two levels. One is endpoint level and midpoint level. For now, I will just select endpoint level and I will select hierarchist approach. So this, then you can include or exclude infrastructure process, or you can include or exclude long-term emissions. I will just uh, leave these for now and just calculate, and I will show you how you can get your results. Okay, so now it will do some processing and then we will get our results from here. It will take 1 or 2 minutes, so you have to be patient. Okay, so here we get the overall impacts. Okay, so you can see normalized results as well. Okay, these are your total results, and these are results with your midpoint at characterization level. And then you can see data tables, you can see the charts like bar graph from here, well as you can go to see inventory, that what are the different components that are included in different process. Like for combustible waste, no impacts are coming from any substance, right? For electricity production, which component is causing most of the impacts, like diesel or electricity from the grid. And if there are more inputs or more uh, components in one process, they will also show all components will show here, and you can see. And then there is process contribution, that which process is contributing towards uh, each towards the total impacts from the process. And then we can see our product overview. Okay, this is our combustible waste that we are getting, and most of the inventory that we are using is from EcoInvent 3 database. So type is material, or whatever you are inventory type is you will see here energy. Some components are from energy, some transportation, processing, everything, all the detail is available here. Okay, so mostly that we use is impact assessment part, and you can just download your copy your okay, it's disturbing me. You can copy your graph from here, okay, and you can paste it simply. You can change colors as well. Or simply you can just copy your results from here, and you can simply paste in any Excel sheet, and then you can play with your results and do different types of analysis that you want to do. So this is how you can model your study. So I will just remove this from the inventory in SEMA Pro. So this is the impacts only from the sorting phase. And then you have to move towards like recyclables and all other things. So for the limitation of time, I will not do it now, but I will provide you inventory so you can play with that and you can do it by yourself. And that will be your assignment as well. I will explain everything in detail that ISWA team asked me to do, and you can use your country specific municipal solid waste composition, and you can just uh, do waste like life cycle assessment of waste to energy through incineration for your own country. Okay, it's just for assignment, like for the sake of assignment. So this will help you to do some practice on life cycle assessment as well. So for now, this is all from my side. And if you have any more questions or you want to ask something, you can always write to me, and you can ask your questions or anything other than this about waste to energy or life cycle assessment of waste. So these are my email address, and I will be sharing these slides with the ISWA team as well. They will share with all the participants, and then you will have my email address in these slides as well, and you can reach me out anytime. So I hope this will be useful for you, and thank you for your attention and time.